Hello, my name is John Gamble, and today I'll be providing training on our SI72xx Hall Effect magnetic position sensors. Hall Effect magnetic position sensors are used in many applications such as industrial and automotive, metering, security and automation, and consumer products. Across the board, the higher sensitivity of the Silicon Labs products means that large expensive magnets can be replaced by smaller and less expensive magnets, or that for the same magnet a wider range of operation can be achieved. The Silicon Labs parts are highly configurable. Things like sample rate and magnetic field thresholds can be optimized to the application. These parts are surface mount compatible, which means in the situation where the customer had been using a reed switch, they can go over to a surface mount type part and get higher reliability and lower manufacturing cost. Our parts are extremely low power, which is of course important in battery powered applications. Our parts are very small in size, and in particular we will soon be offering a 1.4 by 1.6 millimeter DFN package. Finally, for automotive applications, our parts are AEC Q100 automotive qualified. The SI72xx Hall Effect magnetic sensors can be divided into three general categories: the 7201, 2, 3, 4, 5, and 6 switches and latches with optional tamper detection, the 7211, 2, 3, 4, 5, 6, and 7 fixed function output sensors that output the magnetic field strength in either analog, PWM, or cent format, and the SI7210 I2C programmable linear position sensors, which have a high 12-bit resolution and a low 0.1% output linearity. And also this is integrated with a temperature sensor. Common features for these parts are industry-leading sensitivity, with sensitivity as low as less than 0.9 milliteslas, and very low offset and noise. We have the lowest power consumption in the industry, 400 nanoamps at 5 samples per second. Our parts are extremely accurate over temperature, and we have two VDD ranges of either 1.7 to 5.5 volts or 3.3 to 26.5 volts. Our parts are capable of extended temperature range operation from -40 to +125 degrees C, and are AEC Q100 qualified. Going into more detail, let's start with the SI720x 3-pin switches and latches. These parts have a single output pin that goes high or low in response to the magnetic field, and are divided into either switches, latches, high voltage parts, or low voltage parts. The output pin goes high or low at a certain pre-programmed magnetic field level. There's also an option for VDD current signaling, where the IDD goes high or low in response to the magnetic field, making 2-pin operation possible. Tamper protection is optionally available on the output pin. In the case that tamper protection is enabled, the output pin reverts to the zero field level when the tamper threshold is passed. The average IDD for these parts depends on the sample rate and can be as low as 0.4 microamps average, sampling at 5 times per second. Next, let's look at the SI721x field output Hall Effect sensors. All of these parts sample the magnetic field periodically, then output a signal that represents the field on the output pin. In the industry standard 3-pin SOT23 footprint, we offer parts that can output the data as either analog format, PWM format, or cent format. Cent again means single edge nibble transmission, and the cent parts have the option of a built-in self-test feature that can be activated by holding the output pin low. See the datasheet for more details about built-in self-test. These parts are also offered in high voltage and low voltage ordering options. We can customize the sensitivity, sampling rate, and many other parameters at factory test. Again, see the datasheet for ordering options. These parts are kept active at 0.4 milliamps to keep the output pin active. For the 5-pin parts, they can be put in a very low power sleep mode at 0.1 microamps using the disable pin. The SI72xx I2C Hall-Effect sensors have an I2C interface where the operate and release points can be user configured. It's also possible to read the magnetic field strength with 12-bit resolution and 0.1% output linearity through the I2C interface. Finally, the temperature can be read through the I2C interface. Factory configuration options include the I2C address, the sleep mode sample rate, and the tamper threshold. See the ordering guide for more details. It's possible to use a sleep timer with an IDD average as low as 0.4 microamps, sampling 5 times per second, to generate a programmable interrupt when the magnetic field crosses a certain threshold. Then you would wake and read the field data. Or you can put the part to sleep at 0.1 microamps average IDD and then wake the part periodically and read the data for very, very low power operation. Switches and latches are good for telling if a magnet is simply present or not present. For position sensing, where you want to calculate the position of a magnet, there are several solutions available from competitors where 2 or more sensors are integrated and used for calculating the absolute position or angle of a magnet. These solutions are generally expensive and power hungry, with on-chip electronics to go from a calibration lookup table to a calculated position or angle. Our I2C devices are perfect for this kind of application. You can save the cost and power by doing the calculations on the host instead of on the sensor, and you can add tamper indication to the algorithms to support tamper detection with no added cost. Our wheel angle demo shows one example of this. You can see more details in application note 1018, and code is also available in Simplicity Studio in the September 2017 STK release. It's possible to do angle position with resolution of less than 1 degree and position sensing with a resolution in the range of 1 micron with proper magnet design. Absolute accuracy in this range will also depend on mechanical design. This concludes the SI720xx Hall Effect magnetic position sensor training.